Hi everyone, welcome to this session. So up to now, we have developed the concept of basis and something called local basis. Let me talk to you about another important concept. The motivation is similar like basis. So if you see, what is the advantage of studying basis in a topological space? The advantage is, see, in general, in a topological space, the collection of all open sets, that is what you call topology, is a very huge collection, right? So the idea was to understand the whole structure, the whole collection topology with some less or reduced number of sets, right? So similar kind of motivation we can give for subbases too. And you will see these things, sub-bases, bases, local bases, will be a very important what structures or subsets of topology as far as we will go on. So as the terminology suggests, sub-bases, it is some sub of bases, right? Like something prior to basis or something from which we can talk about basis, right? This is what this English word sub basis suggests. So let us see, it is actually that. So let me begin with the definition of a sub basis for a given topological space. So definition of what? Sub basis. So let X tau be a topological space. Okay, and some sub collection. Okay, say script S contained in 2 to the power x. What is 2 to the power x? Power set of x. Is called a sub-basis. We don't put this dash in between sub and basis. We just write sub-basis. S-U-B-B-A-S-I-S. No dash is needed. So in mathematics. So it's called a sub-basis for tau on x, for the topology tau on x, if tau is actually equal to tau bracket s. I hope you remember this notation. We have introduced it earlier. So what is tau bracket s? Tau bracket s is the smallest topology on x containing this sub collection S or stylish S, whatever you want to call the symbol. So, right? So, what is a sub-basis? Sub-basis is a generating set for a topology, right? We have used these terminologies when I have talked about intersection of topology and all. If you don't remember, you can look over it or you can refer any standard textbook or you can ask in comment also if you have any issues with this tau bracket s. So what is tau bracket s? It is the smallest topology on X containing this subcollection S. So this is same as tau. In that case, I will say this S is a sub-basis for tau. So, okay, so let us begin with an example. So consider real line R. Okay, what is real line R? I hope you guys remember. It is R equipped with what topology? The Euclidean topology or the Euclidean metric space, the distance, whatever you want to say. Okay, Now, let us see what can be a subbasis of S. So, of course, I have something in my mind. So, define script S to be minus infinity to A and B to infinity. These kind of open intervals, what you will call these rays, right? So, A comma B in R. What's our claim is? Claim S is a subbasis for real line R. That's what we want to claim. Okay, okay. One observation, guys. Observation. If S is a subbasis for x tau or some topology tau on x, you can write either way. Then S is of course contained in tau and members of S are called, can you guess? You can stop the video and guess, are called sub-basic open set. Sub-basic open sets. Like the member of bases are called basic open sets. So these are sub-basic open sets. So let us go back to our example. What we want, what we are claiming that S is a sub-basis for real line R. You may try yourself, but let me tell you how I want to do this. Okay. So let A comma B belongs to R, be arbitrary. Okay. And say A is strictly less than B. Now observe following. A comma B. So if you want, I can plot here. So, okay. So this is say your A, B. So this is A comma B, the open interval. Okay. Now what I want is consider this set from here to open here. So what is this? Minus infinity comma B. Okay. And consider something else. Okay, what I want to do is, yeah, say let's choose this color and consider this. So what is this? A to infinity. What you should have between these two sets, as you might have guessed, so we will have intersection. So observe this. Of course, it is we can observe from the plotting, and then you have to verify, take a point there and show it's there and like that. That is simple. I'm leaving it as an exercise. So what we have shown that any open interval I can write like this. Okay, let's see then what. So what I wanted to say is, okay, so let's have this observation and call it star. So what I have to show, S is a subbasis for real line R. That is, I have to show that the topology on real line R is the smallest topology containing S, right? So let us denote a topology by something. Denote topology on real line R by. say tau u. Okay, to show tau u is the smallest topology, right? Tau u is tau us. That's what. Sorry, some tau s. That's what we have to show. So smallest topology containing what? This S, what we have defined, right? So I hope this I can leave as exercise because we have done many examples of open sets. So this is actually sitting inside tau u. That's what you can observe. What we have to show, tau u is the smallest topology containing this thing, right? Now, how we are gonna show is, so let tau prime or t prime be any other topology containing script S. What we have to show? To show, see, it's always better to write step by step, even if it consumes a lot of time in the beginning, of course. And then when you become little bit mature, you can always play with the things. So what we have to show? Tau u is actually sitting inside T prime. Okay. Now note that, guys. S is sitting inside where? Tau prime. So this implies A comma B belongs to tau prime for every A comma B in R. Is it right? Think for a moment. So you can stop the video and think. This is by star. No, that's why I just have started with that because I know I need to use it somewhere. But suddenly I forgot that. Okay, let's start from what we have to show, then we can observe. So by star, you see S is sitting inside tau prime. So minus infinity to B, A to infinity is also a member of tau prime, are also member of type tau prime, and their intersection would be there because tau prime is a topology. So in particular, open interval A comma B is a tau prime for every A comma B in R, right? Another observation, note that the collection B, A comma B, A comma B in R is a basis for the real line R. So basis for the topology tau u. So what you have established, that's it. This script B is actually sitting inside tau prime. Sir, what is a basis? A basis is a collection of open sets from which if you take any open set, you can write it as union of bases, right? So this will implies, what this will implies? That tau u is actually contained in tau prime. So we are done, right? We have shown tau prime is the smallest topology containing these open rays, right? So see, if you observe this proof to show that this S is a subbasis, what we have used? We have used basis of real line R. I mean, this is not the only way, I agree, but you see, somehow these subbases and bases are related. No, that's what I said. Sub. So sub means before it. So let us see. Let us understand this. Why we call such collection subbases. So like in bases, how we have done, if you remember, in bases, given a topological space, we established or we defined when we call a subcollection of topology to be a basis. Or given just a set, We have constructed some family, right? Some family. I mean, with some conditions. I'm not restating it. So there were two conditions. Using that family of subsets, what we claim that collection would be a basis for some topology. So similar thing we are gonna do here. I hope this is clear. So let me begin with the terminology sub-basis, why it is given. So let me start with the thing. So let X be a set. One more thing. So these kind of things, if you remember, we have also done in local basis. So from local basis or neighborhood basis, we have constructed a basis for the topological space, and from a basis we have constructed a local basis for every point. Yeah, for every point. So you see, that's how this like kind of going from one thing to other thing to the previous thing. So these kind of things usually happens in topology. I don't want to characterize it by some terminology. So let me just continue with this. So we will see something category and all soon. Not now. Soon means after too many lectures. So I like to go in topology, start topology by points at topology only. So I really don't care at that time of categories if you already know about it. But yeah, later on we will be learning what is a category and all. Okay, so enough of chit chat. So let X be a set and S be a subcollection of 2 to the power x, such that I have a very important condition. The condition is x is actually union of s in script s. See, this is a very important condition. If you don't have this, you cannot proceed whatever I am gonna do is. So let us define something, okay? Define. Define a collection script B. Okay. So what kind of collection I'm gonna define is I want to take finite intersections of members of S. I mean, take a natural number n, arbitrary, fix it, take n many sets from S. If you don't have that is fine, take less. Okay, and intersect them. So this is what M is from 1 to some k, Sm, such that Sm first of all are members of S, the script S family, for every m lying between 1 up to k, and this k belongs to natural number. This k also varies. If you don't have, if you have a uncountable collection, then k is running throughout that. If you don't have, then you can adjust accordingly. What I mean, collect all possible finite intersection. Okay. So what is my claim? That is very important. Claim. Script B is a basis for some topology on X. Now we satisfy those two conditions. If you don't remember it, I think it is one or two lecture before. You can see the condition and then watch the video. Okay. So we have to show that this is basis for some topology on X. So let us one by one do those conditions. So one. Let X belongs to X. What you should have a member of this script B which contains X. That was the first condition. So let X belongs to X. And what is X? X is actually union of S S in script S, right? Guys, what this implies? There exists some S in script S such that X belongs to S. Note that S is what? Just a member, finite intersection. So, in particular, if you observe, script S is also sitting inside basis, right? So, this belongs to script because observe this simple fact. Because we are taking all finite intersection, that counts for one also, right? Right? Good. So what we have shown, we have a member containing that. Second, we have to take two members of script B. Okay. What we have to show? To show there exists a B3 in script B. No, no, and a point here. Arbitrary. Then we have to show there is a member B3 in script B such that X belongs to B3, which is contained in B1 intersection B2. We have done some problems like that. Stop the video, guess this member B3, and will just write it. So B3 is actually B1 intersection B2. We will be done. Completed. So what we have established thus, script B is a basis for some topology. Just a second, I have a little bit cold. Yeah, so basis for some topology on X. Let us denote it by say tau, just tau for a moment. Okay. Of course, this tau depends upon B and the choice of this subcollection S, right? I hope this is clear. Can you guess what I'm gonna do next? It's very beautiful. You will see. Think of it and then restart the video. So this is, see, this is how so beautiful topologies claim. Okay, like this. Claim this scripts S is a sub-basis for tau. Just a second. I'm sorry. So this script S is a sub-basis for tau. See, just have a moment here. What I said, I begin with defining something called subbasis. So a subcollection of 2 to the power x is a subbasis if it generates that topology, or in other words, the topology is the smallest topology containing that. But how I said, I will now give meaning to this. So subbasis, something prior to basis. So from S, what kind of S which satisfies this collection? Such a collection, I constructed a basis for some topology. And what I am claiming now, this script S would be what? A subbasis for this topology. Okay, this topology we have denoted. Okay, let us denote it by something like tau script B. This script B, what we have defined above. So, I hope the picture is clear and the terminology why we are calling it subbasis is also justified. Sorry for this, I just have a little bit cold today. So yeah, let us begin proving this. Huh? So what we have to show, this is the smallest topology containing S. So let T prime be any other topology on X such that script S is sitting inside T prime. What we have to show, we already know it. And see, everything will come. And if you compare with the example I have given you now, the same kind of strategy I have been followed here in this, observations or whatever this thing we are doing, uh, call it a theorem or anything. So to show what we have to show, tau script B is actually sitting inside tau prime. So this will implies what? This will implies that tau script B is nothing but tau bracket S. It means the smallest topology generated by S. Or in other words, S is a subbasis for that. Okay. So what we have to start with? We have to start with a member of tau B, but not any member, right? It is sufficient to show what? It is sufficient to show that script B is sitting inside tau prime. So this will definitely imply tau script B is in tau prime. See, that's all I have done in example. If you observe carefully, where it is, this example, na? Yeah, this example. That's how I have done. I have shown that basis is sitting inside that, right? And this is very easy. Why? So let us take a member. So let B belongs to script B. This implies there exists a M in natural number such that what is the form of B? It is some finite intersection. Of course, of members of script S for every I in 1 to M. Guys, T prime be a topology such that S is contained in script S is contained in tau prime. So this implies, you know what, right? SIs are in particular in tau prime, of course. This will imply tau prime is a topology which is closed under finite intersections. So this is there, right? SI. So this implies B is in tau prime. So you see how simple this is to show. So what we have observed, given a set and a collection with a very important property that X can be written as union of that members of that collection, we have a topology for which that S would be a subbasis. And we have also learned, given a topological space, when I can say something is subbasis, and the terminology is also justified. So let me conclude with what an example, right? So like this example of this construction, whatever the constructions we are doing. So let me use a different color example. I hope you all know what is an ordered set. So if you don't know, take any textbook, basic textbook on say groups or algebra or topology or analysis, you will have this definition. So let X be an ordered set. Some people also call it totally ordered. So that's what I mean. So what I mean is, let me just verbally say it. It is definitely a partial order with the trichotomy property. If I take two elements in X, either X is related to Y or X is less than equal to Y or Y is less than equal to X, means Y is related to X, or x is same as y. So that's what you call trichotomy property. This terminology is in, I think, Robert G. Bartle, Real Analysis. So I can trust you, you know a lot of about ordered sets. And in ordered sets, we can talk about intervals, right? Like we do in R. है ना? So let me define something. So let script S to be these kind of open intervals. Sorry, A, B in X. Okay. So what is this? The collection of, let's say, for example, like you define intervals in R. I'm leaving it as an exercise to actually see the how that this thing is just analogous to what real line R. Now, I just want you to observe one thing. Say script S has, oh no, it's not script S. Say observe. Say X has smallest element, some X naught. For example, X naught. So if you see this minus infinity to A is nothing but this all points which includes X naught and are related with A. All points for that X naught. Okay, let me just give you a description of this. What is this? This is all X in X such that, of course, X naught is related with what? The point X, and X is strictly related with A. What I mean is, if I don't put equal down, so X is not equal to A. That's what. So I will use this strict kind of thing here. And less than equal we use for it may be equal, right? So it is just analogous how we do in R. I don't want to go too much deep into the ordered sets and all. So good. Similarly, okay, let me correct the spelling. Similarly, what about if X has a largest element? X has largest element, not A. So similar thing you have to observe that I'm leaving as a exercise. So what is our claim? Claim S is a sub-basis for some topology where on X, okay, that's what our claim is. So from the above remark, it is sufficient to show that X is union of the members of script S. Observe that it is very clear, no, that X is union of S in script S and S. I am having a Y here. Think about it. So you see, we have an example, right? You will say, just take X to be R. We have already done, right? So why you are telling these things? No, I mean that's a probable question, right? So let me give you a particular example. Okay, first of all, I hope this everything is clear. Okay, something called which you already have known, but let us understand this terminology now. Example: extended real line R. So I'm gonna extend R in some fashion. See, you know that R is ordered with the usual order, right? So I want to give an exercise here, which we have already done above, okay? So exercise, the usual order on R induces means it will give you what? The same topology as on real line induces the Euclidean topology on R. Euclidean. Sorry, this should be. This is a name of mathematician Euclid, so I should start like this. Euclidean topology on R. Oh, by the way, S would be basis for some topology on X called order slash interval, whatever you want to call topology. Order makes more sense. I mean, it's a better word. So order topology. So what my claim is, if you take the usual order on R, that will give you the real line, the Euclidean topology on R. So what is extended real line? Now I want to capture the concept of the biggest member. You know, R is unbounded, right? But I still want to bound my R. So what I want to do is define, say, just let me change the color of my pen. Yeah. Define an order. So you have to verify that this is an order. Okay, I'm just writing on R as follows. Not R, not R. Okay. Union plus minus infinity. Now, what is this infinity? As I told you, I want to capture the things like something beyond. So this is just a symbol rather than this tilted A rotated in some fashion. You can also take C, D, whatever. Okay, on R with this is also denoted by R bar. So that's how I'm extending. What I'm doing, I'm adding 2 points. What I'm doing, I'm adding 2 points on R. Okay, how many points? 2 points on R I am adding. And what is an order? As follows. So this is denoted by R bar. So as follows, x is less than equal minus infinity, bigger than equal minus infinity and less than equal infinity for every x in R. And x is equal to y, the usual order for x comma y in R. So you see, R is not bounded, right? When we consider the usual metric and all, we have studied supremum and infimum. But in this set, R is actually bounded by this symbol, infinity and minus infinity. Okay. So this is another example. And what would be the topology? The topology will be on R is generated by subbases. Let me give you the subbases. What kind of subbases we want to take? These kind of, right? The open rays. Now it's kind of not only open, but yeah, like something like that, right? A, B, in R. So this will give you a topology. Note that the sets like closed minus infinity to comma 1, these are open now in R bar. Okay, this is an R bar. This is happening in R bar. So this is a subbasis for some topology on armor, which we already, as I told you, we call order topology. There is one more topology I want you to explore. So, homework, explore about this dictionary topology. You will have various sources to read this. You can take Mancrae's uh, topology by Mancrae's, or you can have any other standard textbook on topology. Just read about it, say on art. So this is how you look for dictionary. When you search some word in dictionary, so how is it like? First, you see the first letter and then you search for the second letter, and like that, right? You see where your word is. So, this is also like that. Okay, let me define an order on it. So, and explore about things about this topology. So, A comma B is related to some A prime comma B prime. So, either A is less than A prime, or if A is equal to A prime, this will imply, and this less than equal is the usual, this one. I'm just having less than, same less than, but I hope you are clear. This is the new order here. And this A and A prime, we already know how we compare on R. So that is this is that order. So B is related to B prime. So for example, so 2 comma 1 is related to 3 comma say 0, right? Because 2 is less than equal to 3. And say 2 comma 1 is not related with 2 comma 0, right? Because 1 is not less than equal to 0. So you should have either of these two conditions. So I know I have just hinted about this thing, and this is a very beautiful space which we may consider at some other point of time. But right now, I think this is sufficient. So let me just summarize the things what we have done. So number one, given a topological space, what I am doing? SPAC, sorry. We learned what is subbasis. Number two, given a set, we learn what kind of subsets of 2 to the power x are eligible to be a subbasis for some topology on X. So this actually not the first one. Second point has actually make us understand about that why this terminology sub basis is there. Something prior to basis. So let me stop here. I hope you like this lecture, and yeah, it was more little bit theoretically involved, less examples, but it is important to develop concepts like in this fashion sometimes. So, yeah, okay. Thank you very much. See you in the next session.